underscore for helping us out with these things. And I think I'll get started very quickly. Van Fegre is a very accomplished scientist who has been studying climate change and the effect on this region according to the Ecological Survey, and is a scientist, in effect, studying our parks. And I think you're going to find this talk very fascinating, and I think I'll just quickly turn it over.
Okay, well, thank you very much. It's a pleasure to be here today, and I'm going to tell you a little story about what's happened at Glacier National Park. I've been there almost 17 years now. In fact, later this month it will be 17 years. And essentially, we've been looking at this ecosystem in a holistic way for that entire time, looking at the stressor of climate change. And if you look at the kinds of topography that we have in Glacier Park, it's something, of course, that people come from all over the world to see, but it's more important than just for its scenery. About 50% of the water that humans consume on this planet comes directly from mountains. And I don't just mean drinking water or, bottled water. A lot of the bottled water that's controversial now comes from mountains. But I'm talking about irrigation, municipal water supplies, essentially everything. And of course, as you know, we're extremely water-dependent beings. We're not very good at conserving it, and so we need a lot of it. In the West, in the arid West of the United States, that figure is 87%. So we're very, very tied to what's going on in the mountains. That's point number one. Point number two is that the temperate mountain regions have warmed up 3 times faster than the global average, especially at the higher elevations. So they're extremely sensitive. Like the Arctic and the Antarctic, they've shown relatively greater change than the other areas where, say, policymakers live. Not very many people live up in the mountains to see this kind of thing. And so we have both extremely important water supplies that are in jeopardy, essentially, from climate change in areas that are especially sensitive to that climate change. And of course, the dramatic scenery is part and parcel to the concept of national parks, which Americans hold dear. And so they don't like to see their parks changing. This is the Many Glacier Hotel in the Many Glacier Valley, where there aren't many glaciers anymore. And this was put up by the Great Northern Railway in the early part of last century, in the 1920s. And they were trying to get rich Eastern Americans to not go over to Europe for vacation, but to come out west. They wanted them to see America first, and they call this area the Alps of America, or America's Little Switzerland. That's the sort of stylistic attempt to copy some Swiss architecture and so forth. But people come to Glacier Park and other parks with a certain kind of expectation in mind, and they don't like to see it change. And so we have a kind of an iconic landscape here that is representing the kinds of changes that are going on all over the globe, but in some ways they're much easier to see in a place like this. The other part, of course, is that it's tied very much to economics. And if you look in the background here at the tiny little road that you can barely see going across that slope, that's the Going to the Sun Highway. It's the only road that traverses Glacier National Park over the Continental Divide. And every spring we have to plow that out, and you can see a lot of avalanche tracks that go over that road, and so it's fairly dangerous and all. But the entire regional economy is dependent on when that road opens. And so for every day in the spring that that road is still closed, the regional economy is losing about $2 million a day. So it's economically important. It's important to how we view ourselves as Americans and our national parks, and of course it's important for its water resources. So that's one of the reasons that we began this program. Congress initiated this in 1990. That is the U.S. Global Change Research Program, following an enormous heat wave in 1988. In that heat wave, about 450 people died in Chicago alone, and it was 101 degrees in Washington, D.C. when they were debating whether to, do this thing about climate change or not. So Congress was easily convinced that day. They passed that law, and we've been working off of that ever since. So our particular program is just trying to look at the trends in ecosystem processes and try to figure out what's going on that underpins the kinds of changes we're seeing, understand the dynamics better, and ultimately the purpose is to model that so that we have some advance notice, I guess, of the scope and pace of change that we can expect in this nation as a whole, but very particularly for Glacier National Park as, again, kind of one of these representative landscapes for the nation as a whole. Well, when we first got started, we weren't sure exactly how you begin to monitor climate change. Climate is very, very spatially variable as well as variable through time. You know, the joke about if you don't like the weather in the mountains, just wait a minute and it changes. Well, in a way, that's also spatially true, too. This is a map of total annual precipitation over an 18-year period. And the key point here is that all the colors that show all the different kind of precipitation regimes on the eastern seaboard, it shows that kaleidoscope of colors. Every single one of those practically is contained in all the little mountain areas in the west. And so they're incredibly complicated. You go around a corner, you have different climate. In fact, I was out in the field yesterday, and we had extremely cold temperatures and winds. The next valley over, they're hiking in shorts. So how do you monitor climate when it changes through time and space so quickly? And luckily, we have a solution for that, and that is these small alpine glaciers that dot Glacier National Park. And an example of one of those glaciers is above my head there in the back, just below the ridge. That's, see if I have an actual laser pointer. Nope, no pointer. So that's a Swift Current Glacier. And glaciers are ideal for tracking climate change because they, first of all, are very visual. You can't see soil carbon, you can't see other kinds of things, you can see a glacier. So you can track it, you can take photos of it, you can measure it, and it's not controversial because it's there or it's not, it's bigger or it's not. Secondly, they only respond to climate. They don't respond in any other way. Unlike animals that can change behavior, migrate, plants can dry up, set seed, you know, glaciers can't do anything. They just sit there and reflect climate. And they also tend to reflect climate in a fairly moderate way. In a way, they're kind of a statistical averaging entity on the landscape. So, so they're a geologically charismatic kind of organism in a way, but they're also beautiful in a statistical sense because they reflect trends over years and decades, not year-to-year variation in snowfall. So when a glacier is shrinking or growing, it's reflecting climate, not weather, not annual kinds of fluctuations. And of course, as I like to say, the last thing is that they're not involved in partisan politics. So they're kind of neutral in that respect. So here's Glacier National Park. Continental Divide is the yellow line running down the middle of it. And all the little white splotches are the glaciers. The blue ones are lakes. And so what you can see immediately is that we don't have a lot of glaciers or we don't have very big glaciers. This is not the situation you have in Alaska where you have gigantic ice fields with, you know, huge glaciers coming off of that and going down to the ocean. This is an arid western landscape, so the glaciers are quite small. And this is what one of them looks like, the Red Eagle Glacier. And, you know, people aren't really impressed when they see this because they're envisioning these big white masses that, you know, the Princess Cruise Line shows behind their boat and advertisements and so forth when they go up to Alaska. But these are dirty, dying little glaciers. And they're very, very small. In fact, this one no longer actually counts as a glacier. It's become too small. But you can see where the glacier used to be. This is the lateral moraine, which is just a pile of gravel the glacier pushed up and left there when it was much bigger. It used to fill all the space between here and that area over there. And it was also many hundreds of feet thicker. And this basically doesn't look any more impressive than a dirty snowbank in a parking lot at the end of the winter. But nonetheless, it was instrumental in founding the park. These small alpine glaciers were of great interest to George Bird Grinnell, and he described the entire area around Glacier National Park as the crown of the continent. He used a lot of flowery words to get Congress to put that into park status, and he called the glaciers the jewels in the crown of the continent because he's very interested in them, and he really liked them, and so he was very, very attached to them, and believe it or not, one got named after him as a result of that. And he actually came back to his glacier in 1927, about, 40 years after he discovered it, and was shocked to find that it was smaller. So he was very upset about that, because his legacy was melting away and he wasn't even dead yet. So George Bird Grinnell got the park founded, and sure enough, all the early tourists were drawn to the glaciers too. This is a place where you could go see glaciers pretty easily. It was in a dramatic landscape. And consequently, the Great Northern Railway really promoted this, and they sent photographers out. And so you can see here this picture in 1910 of Grinnell Glacier. And one thing to note is that the ice pretty much right here, comes down to the cliff at the top of the waterfall here, and that's about 1,000 feet high. And George Bird Grinnell described this area and the ice, and then he actually took photographs in the late 1880s. And so we have this legacy of photographs to begin looking at. And when we pair those with modern day photographs taken at various times, it is visually compelling, and it doesn't take a rocket scientist to see that they're going away. In this particular case, all of Boulder Glacier has essentially disappeared. And in fact, in this forefield here, you actually have a lot of plants growing. We've seen bighorn sheep grazing there. We've actually seen some wolverines running around there. And so this is actually open habitat for some other animals. But here you can see the tourists lined up to look at this ice cave feature. And because in 1932 it was popular to go everywhere in the park on horse, the guide is wearing these big furry chaps, like they did in Roy Rogers' days and stuff like that. And so it was a big attraction for a lot of the backcountry visitors. But the glacier essentially has disappeared in 56 years. And everywhere you go in the park, you see the same things, such as Agassiz. This is where Boulder is located in the northern part of the park. You can see what's happened to Grinnell Glacier between 1910 and 1998. That entire 1,000-foot thick wall of ice is completely disappeared, and the glacier is actually behind this little ridge here and is separated from the upper glacier. And the same with Sperry, and so forth and so on. And this is another picture that we took just 2 years ago. And Shepherd Glacier has some huge features. If you look in the upper part of the upper picture, that glacier has a lot of these cracks showing and so forth. And the ice is probably 600 or 700 feet thick at that point, and is showing a lot of robust glacier behavior. It's flowing and moving, and it's grinding the rock away. And even the lower lobe is actual glacial ice. In the lower picture, you can see rock bands showing through where the ice used to be, and you can see that the lower part of the glacier is disappeared entirely. Those are simply seasonal snowfields. So it too has largely disappeared. Grinnell Glacier from the top of Mount Gould, there's an intrepid photographer, Heilman, who hauled a 50-pound oak view camera up there with glass plates and everything to the top of this mountain. He got all over the park. In fact, his nickname was Mountain Goat Heilman. And luckily for us, he has hundreds of pictures from the summits and ridges that look down on all kinds of features of the park, but the glaciers show up regularly. And again, you can see there wasn't even a lake there in 1938. It developed through time, and basically Grinnell Glacier is melting into its own meltwater pond. And in 2005, you can see the lake is dotted with icebergs that have broken off the glacier. And so the accelerated rate of retreat is directly correlated with increasing rates of temperature increase. So we've been having temperatures in the last few years that are completely unprecedented in both the historical record and also the paleo record, at least for 6,000 to 7,000 years. So we're experiencing something completely new. Another view of Grinnell Glacier from a ridge. You can see the entire basin was filled with ice, 1940. 2006, it's distant back and melting rapidly. Another view just showing again that it's not just the retreat in a horizontal plane, but also the ice is thinning, it's ablating or melting downward, so the ice surface elevation has gone down very, very quickly, and it's hard to get a scale for this, but this waterfall right here is 450 feet. So that's the scale to keep in mind for this quote-unquote small glacier. We have a repeat photography website. In fact, I have up here some flyers for those of you who want to make them into Christmas cards or something that you can get afterwards if you're very interested in this. But you can just go to the website and download these. And we put this up, first of all, because we're getting so many requests for them. But secondly, it just seemed that this is sort of the touchstone for a lot of people about climate change. Glaciers melting in Glacier National Park really somehow speaks to people in ways that a lot of statistics and numbers don't. And so we've had these used by people in hundreds of countries, even countries where they don't have glaciers. We've had Korean school kids write us about it, and we had my favorite one that I've talked about before is the Italian fashion magazine that downloaded these pictures, and It was a special issue on shoes, so we're not sure what they're doing with it. But we've had it used in a book on aging and a business modeling textbook, and who knows what people use it for. But it speaks to them in very curious ways. So this is kind of a GIS representation of Sperry Glacier getting smaller. The purple is where it was in 1979. It's smaller than that now. And the key point is that this is one of the larger glaciers, and it visually represents what's happened. We had 150 glaciers in around 1850. We had 150 glaciers. In 1910, when some of them were probably small enough to start disappearing, we still had most of that 150. Today we have 27 by our official count, but we will probably be lowering that figure here in a couple of months with some of the new data that we have. And so the vast majority of the glaciers at Glacier Park have disappeared. And the largest glaciers, such as Sperry, are now on average about 28% of the size that they used to be. So even the larger glaciers, which started melting later, have essentially caught up with the smaller ones, and we're looking at their imminent demise. So these glaciers have been on this landscape for a minimum of 7,000 years. It's possible that they've been on the landscape if they'd survived a warm period after the last major ice age, they may have been on that landscape for millions of years, but we know that they've been there for at least 7,000 years. And so we are looking at these disappearing within our lifetimes. So one of the things that we've done is to get better information. We go directly on the glacier because a lot of the previous information was taken with older methods before satellite instrumentation existed. And even the satellite information until just the last few years at 30 meter pixel resolution wasn't good enough for our tiny glaciers. They barely showed up. It was great for Alaskan glaciers and Greenland and Antarctic. So we have to go out on the ice and use a GPS that he's holding there and be able to go and see the difference between the snow-covered rock on the far right part of the picture and the ice that he's walking on, which is rock-covered. And so it does take a little interpretation and always helps if you don't fall in. And this is a GIS representation of Sperry Glacier, and it's a little confusing, but the key thing, the white part is obviously the ice, and the blue is what melted in just a couple years. So it's thinned out, and it's starting to show some fairly dramatic retreat. For Grinnell Glacier, we couldn't walk along the front because it obviously dumped into a lake, so we backpacked these little inflatable boats up, and you see the GPS unit on the person on the right, and paddled across to the ice surface where it's basically the toe of the glacier is floating in the water. And it's a little bit dicey here, which is why we had two boats, one for rescue, because chunks fall off every now and then. And by chunks, I mean up to 5-acre chunks. So it creates a little miniature tsunami in that lake. So that's why she was brave. Not expendable, but brave. And so we got very, very precise instrumentation employed here. And I like to joke about the fact that we can get the dimension of the glacier down to a few inches. And by the time we hike out and download it to a computer, the glacier's already shrunk more than that. So we may be exceeding the precision we really need. This is an aerial view taken, obviously, from an aircraft. And you can see here two big cracks in the front part of the glacier. The glacier is here mostly in the shadow of Mount Gould, and it's pushing out into the lake. And so this is one of those examples where some Saturday afternoon in September, the whole thing broke off and made a million little icebergs all over the lake. And these are all shattered icebergs. The blue line is where the actual glacier toe is. So we sort of visualize glaciers as drip, 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 drip melting. But every now and then it's boom, boom, boom. And we get some pretty big changes. And in fact, that's exactly what's happened in the last 2 years, and is pretty much an indication that the rate of melting is accelerating. The difference between the blue and the yellow there is about 13 acres, and that occurred in just 2 years. And when you look at the size of that glacier, you realize that's 8 or 9% of the glacier has disappeared in 2 years, largely in these big events. And you can see the size of some of those icebergs out there. The gap between the blue and the yellow there in the lake being 13 acres, you can size that up and see pretty quickly that some of those are 2 and 3 acre size blocks of ice. So they kind of look like the Titanic upside down when you're there. We also go out in the glacier to see how deep it is, because of course it's not just how spread out it is, but also how thick it is, the total amount of ice, the volume, or what we call it the mass balance. And essentially just send a signal down through the ice, it bounces up, and you can see that it's pretty deep. It's at 300 feet right now at its deepest spot, which surprised us a little. We didn't realize that the scoop out of the glacier in the rock had been quite that profound. But you can also see that it's very, very shallow in those white areas, and these are the areas that we anticipate will melt very, very quickly in the next few years. And of course the deepest sections will be retained for a few decades, we hope. This is our high-tech approach to getting the depth of the lake with a sonar and a GPS and a mostly willing volunteer. And given that the temperature of the water is just above freezing, because obviously you got 5-acre ice cubes in your drink there, and so it's pretty much, you know, a real chill fest. And so he's actually in a long underwear, a wetsuit, and waders, and we had to reel him every now and then because he's getting hypothermia. But what he did was he started out, and I know it doesn't look safe. It probably wasn't, but the SS Felix, that's his name, Felix. So anyway, I've made the point that these are small glaciers on a global scale, and that's true. But you know, you have a different perspective when you watch your volunteer going out there and getting tinier and tinier, and almost disappearing. And these flatter icebergs are actually leftover seasonal ice that formed on top of the lake during the winter, so they're not deep like the big ones. And so they got blown around the wind a lot. And so we told him, you know, make some straight transects back and forth across this lake. And the wind started blowing, these patches of ice started moving around, he's trying to avoid them, and that's what it looked like. He got chased all over this lake by the icebergs. So. But we found out it's about 187 feet deep, or 67 meters. And so we have to add that volume of water, which used to be ice, to the volume of ice that's still there, which we got with the radar, and then add the volume that we know from the photographs, how high up on the cliff it got and so forth. And when you do that, you find out that 90% of Grinnell Glacier is gone. We have only 10% of the volume of ice now that George Bird Grinnell got to see when he first saw it in 1887. So this is a pretty large change for a landscape like this when you consider that glaciers are supposed to do things in geological time frames, and they're doing them within human lifetimes. The melting continues, of course. This is just a little sample of some of our glaciers that we've been monitoring, and I use this slide mostly to illustrate the fact that Red Eagle, which was 0.15 square kilometers, dropped to half its size in only 5 years. Granted, it was a small glacier, but when you lose half a glacier in just 5 years, you realize that you're seeing the end. And indeed, we use a 0.1 square kilometer cutoff for glaciers, which is only 25 acres. So, you know, your Kmart parking lot's about that big or something. So again, when they get that tiny, they quit acting like glaciers. They become stagnant ice masses. They don't move, they don't do anything, and so they're no longer quote-unquote living ice, meaning ice that's dynamic. So that's a case in point where that's included in that figure of 27, but most glaciologists would argue that you got to take it off the list. So we have 26, and we can go through the list and do this to a number of others. And this is with 1998 data. We now have 2005 data, and it'll drop. So you'll probably hear about it sometime, but there's probably going to be 23 or 21 or something like that. That's just sort of a summary of what I already talked about. But I'll switch in case I said something different. There you go. So Sperry Glacier is our index glacier. And what we mean by that is that we can't monitor all the glaciers in the park intensively. So we've chosen this one to be fairly representative because it's not dumping into a lake. It doesn't have big cliffs around it. And we think it reflects the climate fairly well. And even though these are, again, small glaciers by global standards, you can lose in some of these crevasses in the upper part of this glacier. You could, drop a Greyhound bus inside one of those and not really notice it. So they're still big features. So I won't won't dwell on the methodology, but basically we do a kind of a checkbook balance. The income is the snow you get during the winter. The expenses are basically how much melts in the summer, and the difference is your mass balance, so whether the glacier is growing or shrinking. So first things we have to measure the snow, and the first year it was 7+ meters deep, and we were kind of maxing out our probe pole. That is actually a very heavy-duty avalanche probe pole, but when you put 2 or 3 of them together, it actually weighs about 35 pounds, which is great for shoving it down the snow because then you can get to the bottom, but you also wonder about attracting lightning and stuff. So the next year we had to get more. We had 9.5 meters, so that's over 30 feet of snow. And we have to dig to the bottom. This is where my bad employees get to go. They have to dig all day, and it literally takes 2 people all day, 5-6 hours, to dig through this. She's standing on the surface of the glacier, and everything above them is seasonal snow. And that snow is extremely dense. It's like snow cone snow. We're not talking champagne powder here. One shovelful weighs so much you can hardly toss over your shoulder because it's on its way to being compressed into ice. So it's extremely dense. And it was basically half the weight of water the first year. The second year we got up to 62% the weight of water. So it was pretty heavy stuff. And then we measured that density, and we know how much stuff, that is how much mass, has fallen onto the glacier in the form of snow, frozen rain, and so forth and so on. And then we have to monitor it to see how much melts. And so this is a little steam drill device from Austria, and it's not a drill in the sense that it goes around and around. It just shoves steam through that black hose and just super melts a little hole all the way down through the snow into the ice, and then we put a pole in there and we can just watch everything happening. And the amusing story with this is that we ordered it from Austria, and it's actually on loan from Joel Harper. And he got it and sent it up to the park, lent it to us. We'd never seen one before. So we're actually reading the instruction manual out on the ice here, trying to figure out how to do this. And it's been translated in English, but it clearly has an Austrian spin because they're very worried about you burning your hands and all safety conscious and all that good stuff. And you do is you light a little stove and it melts the snow into water and then pressurizes it into steam in the little containers. So it's quite hot. And they said, stand back and let it do its work. And while you're waiting, put on to cook some sausages. So the Austrian glaciologists are better fed than us. We were eating granola bars, so it wasn't the same thing. So at the end of the season, then we hike towards Enlightenment there. We go out and see if we can find the poles at the end of the season, and this is what they look like. All the snow, that's Joel, who's on staff here at the university, and that is all melt from that year. And so the poles are designed to flop over as the snow level comes down. They're segmented and so forth, just so they don't snap. And so we got a tremendous amount of snow and ice melting. In fact, after all the snow, that 30 feet of snow had melted, then it melted at the top of the glacier 0.5 meter of ice, and for most of the glacier, 1.7 meters of ice. So 1.7 was, about 5 feet or something. So we're losing 5 feet of ice off the surface of that glacier every year. And in the mid-1990s, we'd done a little model saying how long some of these glaciers would last, and we didn't know how deep the glaciers were, so we had to do a little guesswork. This glacier, Sperry, this is an ice radar trace, is from about 30 meters to maybe 45 meters deep. So if you divide an average of 40 meters by 1.7 meter loss per year, of course you wind up with something in the 20s. It's not exactly precise, but somewhere around 25. And this is what we had predicted earlier. This is a animation of Blackfoot and Jackson glaciers, the 2 biggest glaciers in the park. And this is all historical data as they're melting from the earliest shot, and we'll go through this again, through the present about now. There in 2000 is the present. And then you see in 2030 all the white stuff disappears. All the ice disappears, and all the vegetation has moved into the places where the ice used to be, and the forests have moved upslope. And in fact, that bright green stuff is grass. There's no grass in this picture, and there is at the end, because the vegetation obviously is changing too. So this is kind of an independent corroboration of the model we'd put together with the data we had at the time. and it gives us just as scary a story. So the footnote to that is that about a month ago, for an article in Backpacker magazine that just came out in it's September issue, and it came out on August 2nd, go figure. But they asked us to calculate something in that article, and I took the measurements we had in 1998 for Blackfoot Jackson, compared them to the model, and found out that in 1998 they'd almost made the 2010 mark. We're 10 years ahead. And we have 2005 data that, unfortunately, I think is going to show that in 2005, 2 years ago, we were probably at about the 2016 or 2018 mark, somewhere like that, which means these glaciers are going to disappear even faster than we thought, and we thought we were being conservative. And I think that that's one aspect of climate change that has a lot of climate change scientists really scared, and that is every other day, and this is printed out from yesterday's news, you get articles like this: Sierra trees dying faster as climate warms, reefs dying faster than thought, coral reefs, UN, record extreme weather increasing faster than predicted. So scientists have been pretty conservative about all this stuff, and we're finding out that everything is happening faster and more profoundly than we had calculated as little as 2 and 3 years ago with some of the best information we had. And unfortunately, Glacier Park is kind of following that same line. Now, if you look at all the glaciers, perennial snowfields around the West, this is a survey that I'm helping with and actually partially funding. And these are not all glaciers. These are permanent snow and ice bodies, meaning if there's some white on the landscape at the end of the melt season in September, we count it. Whether it's a snowfield or an ice field or actual living glacier, we just want to know how much stuff is there, because that is the hydrologic balance on the landscape. That's the stuff that's still left on the landscape that can eventually melt and fill up our reservoirs. So that's why we're doing it in this particular way. And if you look at some of the actual bona fide glaciers, you see that all of them throughout the West are going down. There are no exceptions. There's one bit of data that we've now corrected on one glacier out of all the hundreds we looked at that looked like it grew, and that was a mistake. It was just, believe it or not, it was a calculation error. It wasn't a measurement error. And so once we figured that out, we haven't found any permanent snowfield or glacier anywhere in the western U.S. that isn't retreating quickly. Now, one of the things that's driving this is not just the super hot temperatures we've been experiencing this past July, which the UN, or let's see, no, NOAA said that it was the hottest July on record, by the way. That just came out. And so the winter temperatures are going up too. And in fact, that is just as important to a glacier as the hot summer temperatures. Because if you have rain up to 10,000 feet like we did last year, a lot of the snow is falling just at freezing. Those glaciers, those snowpacks aren't cold, relatively speaking. And so in the spring, as soon as it warms up, they start melting right away. In the past, they'd be so cold it would take till July to warm them up to the melting point. So that is one of the scary aspects of this, is that we have a combination of things affecting this. It's not just summer temperatures, it's winter minimum temperatures and so forth. Well, one of the things we've realized is that glaciers are providing a very unique hydrologic role for the arid West. And this is just a quick example of how it's important to be making mistakes when you're a scientist, otherwise you don't really learn anything. And this is a model where we predicted the amount of water coming out of watershed just really well, except for this part, where the difference between the observed and the modeled was very large. And we were puzzling about that, because why did it work the rest of the time? Well, when we built that model, we thought the glaciers were too tiny to matter. And it turns out they are too tiny to matter, except at one time a year, which is in August and September, when all the snowpacks are gone, and all you have left are glaciers melting to feed these little ephemeral streams. So when the glaciers are gone, these streams dry up, which is very hard on fish. And it's also hard on water supplies. It's a stress season. That's why we're having more forest fires and so forth and so on. And it's not only important that you actually have the volume, but you also need to have the cold temperatures. And as these basins start clicking out, the blue ones are the ones that we've lost glaciers in over the past century. And so one by one, they've been going out. And all we have left are these dark green ones that are still glaciated. And so those are going to start winking out in the future. And so we began looking at the output from Grinnell Glacier, which had been monitored for almost, 13 years at one point, and then they discontinued it for funding reasons. And so we started that up again, and we found out that already Grinnell Glacier is putting out less water than it used to because it's so small. No big surprise there, but when that line goes flat or gets very, very low angled, it's going to start having significant effect. But the other point is that it's not just having any water at all in those streams, it's that these are alpine creatures. They've all been adapted for cold water. In fact, the bull trout, which is on the threatened list, is a prime case in point. It's like the fish version of the polar bear. It's the charismatic species tied very, very directly to cold water resources. And these bugs, the stream macroinvertebrates, all have temperature ranges in which they can carry out their life history. And so what is optimum for one is actually fatal for another. And so these have each their little part of the stream where the temperature is just right, and the glaciers help maintain that. So what happens then when the glaciers disappear? We did a little simulation and looked at Pumpelly Glacier here. And in the left-hand corner here, you see the present distribution. At least we haven't measured it, but that's where it should be based on the stream temperatures. And the hydropsyche, the red one, is doing fine right under the glacier where it's coldest. Once that glacier goes away, we think this will happen on the right side. It disappears. The water is too warm for it to survive through the summer. The green one, the arctopsyche, loses a lot of territory, a lot of the stream portion in which it can survive. And of course, then the parapsyche wins. It gets more. And so with climate change, some organism is going to win. The question is that the arrangement of species that we want? Because, of course, we attach certain value to things like bull trout, and this is, I think, a key part of the kinds of conservation strategies we're going to have to deal with in the future, where you can't just go and do what you used to do. You've got to integrate climate change now. The bull trout is the native species. The lake trout's the introduced species. They compete. What happens to the relationship between them when the water is lower in volume and it's warmer? We don't think the bull trout will do as well competing for food resources, but also spawning areas. This is an extreme case in Glacier Park where that permanent snowfield that stays there all year long, this is what's left of it at the very end of the melt season, is providing the cold water down through the spawning reach. And the fish biologist that works on this is pretty sure that when that thing goes, this area is going to be too warm for the bull trout to use. And so another basin will suddenly be removed from bull trout habitat, and they don't have enough as it is. And they've modeled this throughout Idaho and Montana, and under even modest climate change scenarios, you see about 90% of the bull trout habitat disappear. So the question then is, should we be spending lots of money to preserve bull trout when their fate is pretty much sealed? These are the kinds of questions that didn't have to be debated until a very few years ago. And right now, in terms of legislation and all the legalities and everything, you're required to try to preserve them. You're required, basically, to put a lot of money into that. So are we going to have to start changing some laws? Are we going to have to make some cuts about where we put money to preserve things? Well, snow is still dominant in Glacier Park. Even though it's warming up, we still get plenty of it. And snow has a very important role to play besides being wet stuff that melts. And one of them is that it drowns trees. You see the little trees that are out in the open area, they're struggling. And in the past, when we had big snowpacks, these trees were under snow for most of the year, so they couldn't grow. Now we're getting snowpacks leaving 2 to 3 weeks earlier. The snowpacks are lighter, and the trees are starting to grow. And in fact, you can see what's happened over the last 50 years with our snow trend. And trees are taking advantage of that. In nature abhorring a vacuum and everything, as soon as they can get in there, the trees do it. And if you look at the upper part, you see that most of that slope is clear of trees except on the far right corner by transect D. If you look down here, you see that not only is the entire slope at near alpine tree line basically just flashed over with trees. They all got started. but you'll see that the trees on the far right side are much larger. In fact, they've grown so much that the canopy is now closed. So this is pretty dramatic stuff in such a short period of time, in this case 73 years, given that that area had been devoid of trees and had been maintained that way for hundreds and hundreds of years. It had been too cold to grow little trees for a long time. Another case in Point Preston Park, where I was yesterday, these ribbon forests, so-called because of the long linear strips, have these nice corridors of subalpine meadow. And that's where songbirds nest, that's where butterflies are, that's where marmots are, mountain goats, grizzly bears do a lot of digging up there. And those areas now are starting to fill in with trees. And the interesting thing is that the trees in the background, the taller ones that are slightly darker, are on average 250 to 300 years old, because we've done tree cores on them. And we thought, well, you know, then there'll be slightly younger ones, blah, blah. Nope. It's like a cleaver went through. All the trees in the foreground are less than 50 years old, and most of them are 25 to 30 years old. Something happened 25 to 50 years ago to suddenly allow these trees to survive. A climate switch occurred. And so it's pretty stark evidence that it's not just glaciers melting, but we're having, you know, vast changes all over the landscape. And you can see that even some of these little trees are moving out right into the open without any shelter from wind by other trees, and they're surviving under heavy snowpacks. We've skied in here in the winter, and the average depth of snow here is 8 to 9 feet. But it's melting quickly enough in the spring that those trees get a chance to grow. And we also have looked at some things that you may have heard about in the news where we have these long-term regime shifts, and people have said, well, you know, a lot of climate change is just these shifts going back and forth. And so we factored those in. This one's called Pacific Decadal Oscillation, or PDO. And in a nutshell, it's just easy to think of it as a big brother to El Nino, except it gets stuck on for 20 years to 30 years and then comes off. And in our area, the snow and the PDO index are inverse in this almost perfect counterpoint. So when the PDO index is one way, we get tons of snow, and it's another way, we get hardly any. And this explains part of that switch that I was telling you about. These little trees got started at the last time in 1976 when that switch occurred. And it makes a lot of sense. And it turns out this is happening all over the West. Well, here's the question. Why didn't it happen at the previous switch, or the one before it, or the one before it? It's because of climate change. So we do have this roller coaster of climate patterns. The problem is it's all slanted up. And so we passed a threshold that suddenly allowed these trees to do this now when they went through lots of PDOs for 500 years and didn't do it. So these thresholds are important because they cause sudden changes. We don't get climate change and responses of mountain systems just very gradually. We get sudden change. And here you can see trees moving up into the alpine tundra area. And of course, this is where these guys live. And you can see all those evil, nasty trees in the background coming up to get them. And so the alpine habitats that Glacier Park is known for are starting to shrink. They're getting covered up by trees, essentially. Well, another part of this, and I'll wrap this up pretty quickly so we can do some discussion, snow avalanches do bad things. This is a train that got knocked over, and it happens fairly regularly. And this is one coming down over one of the sheds that protects it. Amazing that the ranger car happened to be there right when I came down. Huh? So we set that one off, actually. But, you know, the office hours get a little boring in the winter. So. No, it's part of our research. And the reason is that this is one that we intensively studied. That one you just saw, this is it. Okay, it's called Shed 210. And basically, GIS representation on the left side, the actual photograph obviously on the right, and the snow shed where you just saw the truck and the people, and that's a shed right here that protects the train. And so it came down here and popped off that shed, which is pretty effective. But we want to know how frequently avalanches occurred because they play a vital ecological role. This slope would be all trees if it wasn't for periodic snow avalanches coming in, knocking all those trees down. It has to be a class 4 or 5 magnitude snow avalanche to really rip it all the way down to the ground. And so you can see it completely changes the landscape. In fact, it'll dump trees down in the streams and block them up, change all kinds of things. And I won't go into the details, but without that disturbance, one of the factors that is important is the recovery of these snow avalanche paths. Means you get the forbs that animals can eat, the flowers, and everything else. It's not solid trees. And this is where the bears forage a lot. In fact, these snow avalanche paths are called bear elevators because they start at the bottom and they just eat their way all the way up to the ridgetop. And so what happens then if we lose our snow avalanches because we're losing our snowpack? What will be the consequences for grizzly bears? And to make a lot of data very succinct, we found out there are twice as many avalanches occurring as we had any historical records for, because they only record the ones that knock over trains. And in the middle of a blizzard, you don't see all these snow avalanches coming down and doing their work. And in the spring, people often don't go up in those areas. So they're very, very, very underreported. But the trees report them, and they when they're knocked by an avalanche, it creates essentially a bruise or scar. And you can read that later on and find out the year that a big avalanche hit that tree. So you can reconstruct avalanche frequency. And this is a map showing that the higher up the slope you are, of course, the shorter the return interval, meaning avalanches occur very frequently. The lower down the slope, the less frequently. And that shed, the train shed, is that black rectangle at the bottom. And so it's in an area there that would be, every 11 to 14.2 years. So, about a little over once a decade, it's going to come down and knock trains off on that particular one. There's, of course, 48 snow avalanche paths, so it means almost every year one of them is going to go. But what this means is ecologically, these upper areas have to have that disturbance. They have to get whacked by snow avalanches, or there's no more bear food. And so we also looked at fire, which is another important one, and essentially found that fires in our area, if you look at the bottom panel, are increasing in frequency and size. And so we're getting bigger and bigger spikes of the size of the fires, and they're starting to occur more often. And this is a direct result of warming and drying. And of course, we're experiencing that now with fires surrounding the park at the moment that are 40,000, 30,000, 20,000. We have 3 fires, near the park. And this didn't used to occur. This is historically unprecedented. And this is what our landscape's being transformed into. So right now on the western side of the park, about 30% of the landscape looks like this now, and it didn't only 10 years ago. So huge changes, and not just in firefighting policy, it's just these fires are becoming large and they have a lot of fuel. Well, another thing is extreme events. This is the 2006 flood. If you know Glacier Park, that's Mini Glacier in the back, and you can see the bottom floor is underwater. And it overtopped the road and the dam and gushed down, caused all kinds of damage, including knocking out a part of the Going to the Sun Road that I drove over yesterday, and there's a little rickety metal bridge that you drive across where there used to be a railroad. And these are the kinds of extreme events that are starting to pound the park. In fact, here's another case in point on the Sun Road where these 2 mega monolithic blocks of rock came down and impaled the road. And you can see with the SUV for scale that they're 2 to 3 times larger than that. And you can't move that with equipment. You have to blow them apart. There isn't any machine big enough to haul those things off. Well, if you're getting 40-ton projectiles hitting a road, something's going on, because this has been engineered and has been used since 1929 when they started on. It was completed in 1932, and they haven't had that kind of damage, and they've gone through a lot. So these mountains are starting to shed bigger blocks of rock. We're having more floods. We're having debris flows, et cetera, et cetera. And most of these are related to more extreme weather events, to the warming of the mountains, so the permafrost isn't hanging onto this rock, the disappearance of the snowfields, and the disappearance of the glaciers. So to conclude, how do you put all this information we've gathered together? And this is where we've partnered up with Steve Running on the campus here. And he puts together pretend ecosystems, and this is one of them. This is Glacier Park in a computer brain. Lake McDonald is the blue worm down there, and you can see the mountains. And we've just done a lot of querying with ecosystem models saying, what's the future like? And this one in a nutshell is a simulation where all we did was make the weather weirder. We didn't change the average. We didn't warm it up. We just made it vary more. And what we found is that's really important. And so on the eastern side of the park, which is the St. Mary drainage, you can see by all the orange and stuff, it's negative NPP, which is net primary productivity. What that means is the plants are growing less stuff. They're doing less. They dry out. We lose trees. We gain grass. On the western side of the park, on the left, it's greener. The trees are growing faster. we have more fuel for forest fires, for instance. And this is just due to being more variable, not increasing anything at all. So climate changes in many different kinds of dimensions, and they're all important to habitat for creatures like this that depend on a certain kind of variability. So it's not enough to just look at the average. You have to look at a lot of climate parameters. And these guys are looking at a climate parameter right there in the form of a big firestorm. And this is because we have huge amounts of fuel that have grown during cooler, wetter times, and now we're drying out. And no amount of firefighters can stop some of these conflagrations because you're looking at a legacy of hundreds of years of tree growth. And this is one of them. These are the two fires that occurred in 2003, except these were simulated by a model in the late 1990s. So the computer was pretty darn good. I wish it could predict the stock market for me. But these two fires actually occurred in almost exactly these dimensions with these kinds of intensities. And the computer didn't know they were going to happen. It was about 7 or 8 years before the fires actually occurred. So it means that some things, though, we can begin to predict. We can start looking at where fires will occur, their relative probabilities, their relative intensities, and we can do things like not build buildings there. Now, we also looked at how variable it was across the entire Pacific Northwest, not just the park. And so we looked at some of these other areas. And basically, I'm just going to skip through these for the sake of time, but basically what we can do is we can start figuring out where Doug fir is going to grow in the future. And it's going to move around the landscape. It's going to move to new places. And we can look at how plants will get hammered by early frosts or by later frosts, for instance. And we can look at things like this, which is the climatic controls of vegetation across the entire Pacific Northwest, and say, under this scenario, here is where you're going to have things growing more, and here's where you're going to have things growing less. There are a lot of people, including agricultural interests, forestry interests, municipal planners, that want to know these kinds of things. And ecologists do too, of course. And so this is one where we ask the computer, where is it going to dry out the most? And this is the water output from a landscape. And in a nutshell, the middle part, which is eastern Washington, that's all yellow, doesn't change much because it's already hot and dry there. You make it a little hotter and drier, the plants are already adapted, not much changes. But the red areas are very sensitive. Why do they change so much? Well, these are the mid-slope areas all throughout the Pacific Northwest, not the valley bottoms that don't change as much, not the tops, which change, but not in terms of water balance. It's the mid-slope areas that are drying out the most. And these are, amazingly, where our national forests are, and also where our forest fires are. And these are the areas of greatest change, as we've already been seeing. And this is what's happening. We're getting snow water equivalent, meaning the moisture content of the snowpack. All the red dots are places where it's going down dramatically. And again, this is showing that all of the lowered snowpacks are melting earlier in the spring. So we have less of this to go around, and this is the consequence. And so this is this is the Red Eagle fire last year in August, and I was working on this side of the mountains, and I saw this thing happening, and I thought, well, World War III happened. And we thought we were going to get burned out and run for our lives, but it stayed on that side, but it was really, really impressive, and it wasn't even that big a fire. Well, to add to all of the ecological change, then we have humans come along, and we're changing where we like to recreate, where we like to work, and one of the problems is the wildland-urban interface that you all know about, and people are building their homes right next to flammable forests, and this is my house. So we were evacuated about 20 minutes after this photo. You can see the fire coming. And basically, although this is taken from another part of Montana, that's what it looked like that night. And that entire slope went up. Deer and elk were running all over the place. They actually found a crispy black bear afterwards that didn't make it out. And so it was pretty darn impressive. And it's changed the landscape out our front window quite a bit. So in conclusion, these trends, and this CCE is the crown of the continent, it's kind of the whole area of Glacier National Park, are all pretty much happening already. You can read through the list, but most of these things, to some extent, are happening, and they're beginning to accelerate. And so I think that what we're going to be doing as decision makers, as voters, as taxpayers, is grappling with some pretty big changes in the American West, particularly, in how we live on this landscape. We are not going to be able to do what we've done before, and a lot of the kinds of changes we need to make will take some time. Just changing laws, you know how long that takes. Well, we are moving much more slowly than the environment is being changed on us. And I think that we're going to have to start coming to grips with that, because the documentation we have and the fact that almost everything is occurring faster than we predicted, with no end in sight to that, is something that humans don't cope with well. They kind of extrapolate linearly, and what we're seeing are thresholds where it goes like this and then it boom, changes radically into a new kind of fire regime, hydrologic regime. We're seeing species that just suddenly disappear from our area. They don't gradually go down. They just 1 year, we can't find any of them. This is happening throughout the West. So these are the kinds of things that we're going to have to start looking at, including our entire concept of what a national park is and what Americans want to do with that. So anyway, that's it. Yes?
When was the last glacier for the gas? Obviously, was quite different. When do you think the last glacier ceases to exist in this national park?
Well, I think that we will have functional glaciers only until about the mid-2020s. And what we'll have after that are these little scraggly pieces that really don't count as glaciers, but they are glacial ice. And those could last a while in some of these deep shaded pockets in the mountains. But I think that we will beat the prediction of 2030 for functional glaciers. And while you can debate when a glacier is actually not a glacier, one of the key parts of this for us is that they're so important in the mountain hydrology that long before the last one winks out, their function, their purpose essentially, will have already been eliminated. So that's kind of the consequence that bothers me personally. Yes?
The research is pretty impressive. Are your resources for research going up or down or staying the same?
Well, ours has actually been basically frozen in time for about 10 years. So with inflation, it's actually less. But we are seeing a lot of noise in Congress right now to greatly expand climate change research. And I think that's, there's always some political motivations in these things. I think for the most part, it's because the consequences are so obvious. When Katrina hit, a lot of people attribute that to climate change, and it was very, very dramatic to see opinion polls about climate change before and after that. Even though that couldn't necessarily be ascribed at least 100% to climate change. But some of the things that we're seeing now, like you don't have enough water, or your forests are going up, these things can very directly be attributed to climate change. And because that's fairly dramatic, you're beginning to see a lot of political change in wanting to cope with this. They don't want to necessarily overreact to something that some think may not be a problem, that'll all go back to the way it was. But on the other hand, politicians don't want to look like they got caught with their pants down either. So they're trying to start moving in that direction. So I anticipate that our climate change research will not go away. It's more likely to increase, I think. So, any other questions? I'll stay here a few minutes. I don't know if your period ends now or not, but I do have a couple resources up here. If anybody's acutely interested in something, I have a couple CDs with some science papers on it. If you didn't go to sleep now, you can definitely go to sleep with those. Some contact information with the photos and things like that. We just recently published a book on the crown of the continent with 39 authors from Canada and the U.S. Looking at basically Glacier National Park and Waterton National Park on the other side with Canada, and how it's changing, not just the climate change, but all kinds of socioeconomic changes and everything else. So that kind of takes climate change and adds to it other social change forces as well. So, yeah.
Are there research programs like this in any of the other parks?
There are a few. The Park Service used to have more. There was reorganization, a whole bunch of things. But basically there's about 5 or 6 like this. And most of those have formed into a consortium called the Western Mountain Initiative. because the ones that survived tended to be in the West where climate change is having really big impacts. And so we now work as a group, and we meet once a year and coordinate studies, and the objective is to show how mountain systems are responding in common to climate change. But of course, each of them are a little different, so we want to know what the differences are as well. The Sierras, for instance, react a little differently than we do to drought, and so we want to be able to fine-tune our general kinds of mountain responses to climate change. So, and it's leveraging resources too. We're more efficient that way. So.
Let's thank Dan for coming